it's my great pleasure to introduce Professor Adam Glesser, who's gonna share with us some light on what are we doing today?
How about I'll just take it from there then?
Oh, okay, yeah, sure.
So I want to tell you today about integrating to compute series. So let me remind you of something. If you were here last week, you saw this, Dr. Casper put this into his talk, and I'm sure this will not come as a shock to you. So if I look at this series, x to the n, what kind of series is this? Maybe it'd feel better if I wrote an R instead of an X.
Geometric.
Yeah, now it's also a power series. That also would be a good answer to this question. But yeah, it's a geometric series. All right, and so we have a very nice formula for this geometric series, provided, right, there's some condition here on X, that the absolute value of X is less than 1. So this series converges between -1 and 1 for X, and when it converges precisely to 1 over 1 minus X. Now here's the problem. When you're in, say, a Calculus 2 course, and you learn all these convergence theorems, with the exception of this geometric series, all the rest of them just tell you that a series converges. It doesn't tell you what it converges to. So what do we do when we have a series and, say, for example, the Putnam asks us to compute the value of the series and it's not a geometric series? So what I want to show you today are two techniques for computing the actual value of a convergent series by getting integration into the game. All right. So the first technique is going to be recognizing the series as a Riemann integral. So this is actually something in a Calc 2 course that you do see, but maybe you're not usually thinking about turning your series back into a Riemann integral. So just as a quick recollection, what do I mean by a Riemann integral? So I mean the one that you're going to see when you take, calculus out of Stewart. So if I integrate from a to b a function f, then what do we do? Well, first you chop up the interval a to b into little pieces, right? And we're going to make them evenly spaced. Each one maybe has length, say, I don't know, some length delta x. And so this point over here would be a plus delta x, and then this would be a plus 2 delta x, etc. It's really inconvenient to write it this long. So usually we'll write something like, okay, maybe this could be x1 and this could be x2, so forth. Maybe this is xn if there's n subintervals. And then I might start at each of the right endpoints of these subintervals and evaluate the function, right? So I'm going to sample the function at the endpoints of these intervals. So this would be a right endpoint approximation. And so what I'm going to do is take f and evaluate it at all of these right endpoints, and then multiply by the width of the interval, right? Because when I multiply by the width, I'm going to get, right, this little rectangular area. And so multiplying by delta x will give me those areas. Of course, then I'm going to add these all up. K goes from 1 to n. And this would be a right endpoint approximation. Right? And then if I want to define this integral, I take the limit as n goes to infinity, provided this limit exists, right? Sometimes limits don't exist. So here, delta x is the width of these intervals, and you could write that down in a formula. I usually don't like to, but you could. All right, and x sub k, that would be a plus k times delta x. Of course, you could start at 0 and go to n minus 1, and then you'd get a left endpoint approximation. We won't use that one today, but I'll give you some supplemental problems at the end where you could use that left endpoint approximation. Okay, so that's probably something most of you all have seen in your Calc 2 courses. So that's kind of our first thing. So our second thing here is, let's just jump into a problem now. I want to compute the limit as n goes to infinity of the following sum. So k is going to go from 1 to n, and I'm going to have n over n squared plus k squared. So this piece right here, that looks awfully similar to the Riemann sum definition, right, or the Riemann integral definition. So what I would like to do is rewrite this fraction here in a form that matches what we expect to see in a Riemann integral. So let's take a look over here at n over n squared plus k squared. Let me factor out an n squared, all right, from the bottom. When I factor out an n squared, I'll get n over 1 plus k over n squared times 1 over n squared. Okay, an n and an n squared are going to cancel. And so I end up with 1 over 1 plus k over n squared. I guess I don't need those parentheses, times 1 over n. And so now let's just draw this little picture here. When k is equal to 1, this piece right here is just 1 over n, right? That's just a little bit past 0. So I have 1 over n. And as k increases, this becomes 2 over n, and then 3 over n, and so forth. And at the very end, k is equal to n, I get n over n, which is 1. Each of these little pieces has width 1 over n. So I'm exactly looking at what would happen if I was doing a Riemann integral, right? The width here is the 1 over n. The function is 1 over 1 plus, well, this is where the value, right, goes into my function. That's my x squared. And so I can rewrite this as an integral from 0 to 1 of 1 over 1 plus x squared dx. All right, well, we got a nice comment in the chat. Let's see. The left and right endpoint approximations are supposed to converge to the same value as n approaches infinity, but are there some circumstances where one is preferable to the other? Does it just have to be with how nasty or nice one looks compared to the other? Yeah, that's a great question. So yeah, it very often is dependent on the situation you're in, why you would want to choose one side or the other in a particular application. So in this problem, because you can see I'm starting my k at 1, I really don't want to use a left endpoint approximation here, right? Because my first sample value is actually at 1 over n. I'm going to send some notes to you all at the very end of this with some other problems to work on, and you'll see at least one solution where it's much better to use the left endpoint approximation because it starts when k is equal to 0. All right. So this is a key idea here. What we did. So questions about how I went from this limit now to this integral. While you think about a question, I can quickly write down an answer because this is a routine problem from Calc 2. We know an antiderivative is arctan. Arctan of 1 is pi over 4. Arctan of 0 is 0. And so we actually get a solution to this problem. No questions? Okay, why don't we try another one then? We'll try something similar. So
there's a question in the
oh,
chat now. Sorry.
here we go. Yeah, there we go. Okay, how do we go from k over n quantity squared to x squared? Right. So in our definition, right, we're evaluating the function at, right, whatever these input points are, right? X sub k here, right, was a plus, you know, k delta x, whatever. So here, if my function, so if my f of x is equal to 1 over 1 plus x squared, then what would happen if I evaluate this at each of these points? So f of 1 over n would be 1 over 1 plus 1 over n squared. F of 2 over n, this will be 1 over 1 plus 2 over n squared. All right, continuing on, if I had f of k over n, this would be 1 over 1 plus k over n squared, which is precisely, right, the piece that I have. So I'm basically kind of working back and going, okay, what would be the function such that when I evaluate it at k over n, I get 1 over 1 plus k over n squared. Right? And I say, oh, well, 1 over 1 plus x squared, that will do it. Because I'm evaluating x at k over n. Does that help?
Yep. Thanks.
All right. All right, so let's try another one here. Maybe I'll move this down a little bit. So I want to, this time is actually, the series is, I'm going to write it out a little bit just to make it, I don't know, feel easier to read. So this is a really weird one. I'm going to take e and I'm going to raise it to the negative 1 over n power. And then I'm going to take e and raise it to the negative 2 over n power. And then e to the negative 3 over n power. And I'll keep going till I get to e to the negative n over n power. And n is going to go to infinity. But I'm not done. No, that's not hard enough. We're going to, on the bottom, put sine of 1 over n, and a sine of 2 over n, and a sine of 3 over n, etc. And I'll finish with a sine of n over n. So I guess this is maybe a mean problem to give to Calc 1 students. Almost certainly they're going to, I guess, try to use, I don't know, L'Hopital's rule in some weird way. Not that it works, I'm just saying they'll try. But if we isolate the top and the bottom from each other, this should look very similar to what we just did. Right? It's only missing one little piece. So if I look at the numerator, so this is a sum. Everything looks like e to the k over n. K rather goes from 1 to n. And then we take a limit as n goes to infinity. So this piece definitely looks like the beginnings of a Riemann integral. This looks like I'm evaluating a function at k over n, right? What would be the underlying function here? Well, I guess probably something like f of x equals e to the negative x. All right, and then you can evaluate it at k over n. What's the one thing I'm missing, though, to have an actual Riemann integral?
Your delta x.
Yeah, I don't have my delta x. Now, I know what my delta x should be. As I increase k, each time this is increasing by 1 over n. Okay, so I really want to have a 1 over n out here. I don't, but I want to. Okay, I wish I had that. Okay, well, you know what? I like to cheat, so I'm just going to pretend I have that. If I do have this, then I know I can rewrite this as an integral. So let's see, what are the bounds? When k is 1, we get 1 over n. So this looks the same as before, right? I'm starting at 1 over n, and I go all the way up to when k is n, I get n over n, which is 1. And of course, 1 over n is just a little bit above 0. So I must again be going from 0 to 1. And I have e to the negative x dx. And okay, this is a pretty straightforward one. Antiderivative is negative e to the negative x. So evaluated at 1, and we get negative e to the negative 1 minus, okay, let's evaluate it at 0. Okay, e to the 0 is 1, so we get a negative 1. So this is 1 minus 1 over e. Okay, I cheated, right? But maybe if I make this problem go on long enough, you'll forget I cheated. That's my goal. Okay, let's look at the bottom now. All right, on the bottom, I could write it as a sum. K goes from 1 to n, and now I have sine of k over n. And again, we take a limit as n goes to infinity. Okay, once again, this looks very, very much like a Riemann integral. What would be my function here, right? Maybe I'll call it g. What would be the function that I should be using?
Sine of x.
Sine of x, right? That seems right. Okay, but of course, once again, I'm missing this delta x bit. Yeah. Oh, and Jorge seeing what's going on, right? So if I just toss it in again, then I can do this integral. Okay, well, we can do that reasonably quickly. So this will be the integral of sine of x. Okay, I guess that's what, negative cosine of x from 0 to 1, which is negative cosine of 1 minus, okay, what's cosine of 0? Right, cosine of 0 is 1. So this will be minus 1. So I get, again, 1 minus cosine of 1. So in the chat, Jorge add this question. If you're missing the dx, okay, so he's thinking about this delta x here from the top and the bottom, don't they end up canceling? Yeah, what if I just went up here and said, okay, let me multiply by 1 over n on the top and the bottom. I put what I'm missing in, right? I fix the cheat by putting them in twice, once in the numerator, once in the denominator. All right, and that's totally legitimate to do. N is not equal to 0 here. Okay, and so we can immediately write down the answer now. 1 minus 1 over e over 1 minus the cosine of 1. So just by knowing what we want the form to look like, right, knowing that this Riemann integral is out there, we can play around a little bit and get it to look exactly like we need. And then the computations become quite reasonable. All right, questions about this technique? As I said before, at the end, I'm going to send you a file. It's going to have several more problems that you can practice using this technique, as well as it'll have full solutions too. So if you get stuck, you can look those up. Okay, let's move on then. I want to show you the second technique for today. I'm on OneNote. You're going real slow today. So technique 2. Oh, yeah. All right, we're going to jump away. Oh, here we go. Something in the chat. So if you mean, you could start by having the quotient of 2 integrals and then putting them in Riemann sum form, and people would be freaking out. Actually, that's kind of a fun game to play. Okay, hold on. Let me just switch stuff for a second. I think my screen is unhappy. Okay, there we go. So technique 2. So I struggled coming up with the good name for this technique. So I'm calling it artificially including integrals in your series. Okay. So this is going to feel a little weird, but this is actually going to, in many ways, extend the geometric series test in a pretty wild way. So I want to start with something which I call the reciprocal translation lemma. Which is a very fancy title for a very simple statement. So if you have some m which is not equal to 0, you'll see why I can't be 0. In fact, you'll see right now, m should not be 0. Then the reciprocal of m, 1 over m, is equal to the integral from 0 to 1 of x to the m minus 1. Which seems totally absurd to do. I mean, you will see how to prove this very easily, right? You take an antiderivative, you get x to the m over m, you evaluate it at 1 and 0, and you get 1 over m. Yeah. So it's not at all hard to prove, but why? You're sitting there with the fraction 1/3. Why would you want to write it as an integral? That's not generally a smart thing to do, right? On the other hand, this is kind of how mathematicians roll. You were sitting around, you learned the number 1, you thought 1 is pretty nice. And here, what do mathematicians do? We like to rewrite it as cosine squared plus sine squared, all right? Or as the sum of 1/2 to the n, right? As n goes from 0 to or from 1 to infinity, right? Like we just play these games. Okay, but I'm going to show you how we can actually use this in a pretty neat way. So I want to compute the following series: 1 plus 1 over 9 plus 1 over 45 plus 1 over 189 plus 1 over 729. And I assume it's perfectly obvious how I'm generating this series. You're very, very bright if you can see it. So let me show you what's going on with these denominators. So I'm going to start factoring these things. So 9 rather is 3 times 3. All right. 45. Well, that's going to be 5 times 3 times 3. 189. Okay, let's see. 7 goes into that, and 7 goes in, let's see, 27 times. So 7 times 3 times 3 times 3. How about 729? Well, 9 goes into 729, and it goes in 27 times, or 81 times rather. So it's 3 times 3 times 3 times 3. So here's the pattern you might be seeing. I have odd numbers, and then I have increasing powers of 3. Right? And so I could rewrite this if I preferred as this series, odd numbers. Okay, I'll use an odd number piece, and then I have powers of 3. Okay, and let's just double check. So like when I get to the 5th term, I should have 4 3s. Yeah, there we go. And I should have the 5th term, I should have 9 as my odd one. Yeah, 2 times 5 minus 1 is 9. Cool. Okay, it turns out the problem isn't to rewrite this as a series. The Putnam is never that easy. But, okay, so we do this. If I could somehow cover this piece up, and I just had 1 over 3 to the n minus 1, boom, I've got a geometric series, and we win. But, well, I can't just cover up this piece. So instead, what I'm going to do is use the reciprocal translation lemma to rewrite this 1 over 2n minus 1 that I don't like as an integral. So 1 over 2n minus 1 by the reciprocal translation lemma is equal to the integral from 0 to 1 of x to the, okay, it says I take this number and subtract 1 from it. So 2n minus 2. And 2n minus 2, that's the same thing as twice n minus 1. Okay, so, but this isn't the fraction I want. I want 2n minus 1 times 3 to the n minus 1. Okay, but 3 to the n minus 1, I can just push that inside the integral because there's no x's in here, right? It's just a constant. And so when I put it in, look what I get. I have an x squared to the n minus 1 divided by 3 to the n minus 1. So I can actually rewrite this as x squared over 3 to the n minus 1. So by using this reciprocal translation lemma, I've been able to recapture something that essentially looks like a part of a geometric sequence. All right, so now we can rewrite our series. So the series that we want to compute is going to be this series where I now replace the terms with this integral. Ooh, wouldn't it be nice? Wouldn't it be nice if we could move that sum inside the integral? Oh yeah. It would be amazing because then we would be able to sum this geometric series, right? Well, we can do it. Now, I'm not going to go through all the details of switching infinite sums and integrals here. But I'll just tell you, as you are trying to prepare for the Putnam, there is a couple of integrals, or rather theorems, I would suggest that you look up. One of them is called the dominated convergence theorem. The other is called the monotone convergence theorem. And they allow you to swap the order of summations, right, and integrals, provided some conditions hold. You won't need to know the proofs of those things on the exam, but when you're writing up solutions, it's very good if you can say, oh, and I can switch these because of the dominated convergence theorem. So in this case, I actually did use the dominated convergence theorem, which will allow me to switch these two. All right. One quick adjustment. This is starting at 1. I'd like it to start at 0, but that's okay because I can add 1 to this to subtract 1 from there. So this is the same thing as going from starting at 0, but then raising it to the nth power. Yeah, you're right. It's just easier I mean, it was very easy for me to see dominated convergence in this case, but you're absolutely right, Dr. Casper. Okay, so now we can actually use the geometric series test and sum this infinite series. And we'll get 1 over 1 minus x squared over 3, provided, right, we're going to need here that the absolute value of x is less than 1. But that's okay, right, because look, we're only integrating from 0 to 1. So that's not a problem. Okay, and everything from here now is what we're going to call Calc 2 routine. All right, if you're only in pre-calculus, that's not routine. But if you're in Calc 2, this should be routine. So we can rewrite this, right, just by doing basic algebra here. And what should we get? Let's see, 3 minus x squared over 3. So we flip it. And when we flip it, we get 3 over 3 minus x squared. This bottom will factor, right? Not in a nice way, but in a good enough way. Right. And I don't want to spend the time going through all of this computation, but if you have 3 over root 3 minus x times root 3 plus x, what technique am I going to use if I want to integrate?
Partial fractions.
Yeah, right. We'll use partial fractions. So let's come over here. We're wasting all this space. So use partial fractions. So what are we going to end up with? So I'll tell you, a root 3 over 2 comes out, and you end up with a 1 over root 3 minus x plus a 1 over root 3 plus x. And so this ends up being, let's see. You integrate this thing, you're going to get a negative natural log of root 3 minus x. And you might say, hey, don't you need absolute values? But of course, x is between 0 and 1, so that won't be an issue. And then we have an ln of root 3 plus x. Okay, and there's some amount of plugging in, which you can either look at the write-up I did or just work it yourself, which is a better exercise. And you'll end up, at least with a little cleverness, with this fairly compact, tight solution to the problem. Let's see what we got in the chat here. Whoops. So if we, okay, so what you're saying is, one, if we have a geometric series, we can turn it into an integral that is hopefully easier to compute. And two, if we have a series that can be turned into a, man, every time I click a button, it's moving down, can turn into a geometric series times some constant, you can likewise turn it into an integral. So of course, as with everything, is it depends, right? But that's the goal, right? Is if you start with some geometric series and there's some sort of complicating factor, right? And it is just some sort of a constant in terms of n, we can, right? Particularly if it's in the denominator, right? We can write this as an integral now. And that integral is going to have that geometric sequence flavor, right? It will be a power of x. Now, whether or not all these exponents line up nicely, that depends on the problem. Of course, you may be able to manipulate it even if they don't line up nicely, and okay, pull some junk out so that they do line up right. But that's the idea, is right? We start with the geometric series test and we want to go a little bit further. In Calc 2, you learn how to maybe integrate or differentiate those things to allow you to compute some series for things that don't look immediately like geometric series. And here, this is another technique, right? Using this reciprocal translation lemma. Okay. Cool. All right. Now, what I would very much like to show you all, I need one preliminary result for, and I think this is pretty neat. Something that we don't typically get to talk about in Calc 2 is, we talk about infinite series all the time, right? So you're adding up an infinite number of things, but something we usually don't talk about are infinite products, right? And partly, it's a more complicated theory, and of course, it's very hard for an infinite product of things to converge. I mean, okay, if one of them is 0, you win pretty easily, but if they're not 0, then it can feel pretty tough. But what I think is actually quite amazing is that, okay, let's go back here to our geometric series. So we know, provided that the absolute value of x is less than 1, that this geometric series converges to 1 over 1 minus x. But it turns out there is a product form of this. And the product form, you have to take things of the form 1 plus x to the 2 to the n power. Now, in the formal write-up that I'll send you, I give a very precise proof by induction of this, but let me just give a quick argument as to why this should work. So if I start with 1 minus x. And I multiply that by the very first term in this product, right? When n is equal to 0. So I'll have 1 plus x to the 2 to the 0. Well, 2 to the 0 is 1. So this is just times 1 plus x. And the next piece would be 1 plus x to the 2 to the 1. So this would be 1 plus x to the 2 to the 1. Well, 2 to the 1 is just 2. Okay, and the next piece, when n is 2, I'd get 1 plus x to the 2 to the 2. 2 squared is 4. You start to see the pattern here, of course, right? 1 plus x to the 8, and 1 plus x to the 16, and so forth. So this is almost the same product, but I've hit it with an extra 1 minus x. Now, here's the just outrageously cool thing. What happens when you multiply these first two factors together?
You get 1 minus x squared.
Absolutely, right? This is the so-called difference of squares formula in action.
Yeah.
My favorite algebraic formula. Okay, well then what's the next thing? We have 1 minus x squared times 1 plus x squared. So what will that be?
1 minus x to the 4th.
1 minus x to the 4th. Oh, wow, look what's happening. 1 minus x to the 4th times 1 plus x to the 4th. Yeah, right, Jorge? This is just so neat. First time I saw this, I almost fell out of my chair. It's just like, what? How could that be? But it works. Yeah. Okay, and we keep going. Right? We keep going. So if I stop, right, at some point, right? If I stopped at any point, so let me say I called PS of x, right? Let's let this be the partial product. So I'm going to stop. I'm going to stop at some s. All right. Well, if I multiply this by 1 minus x, okay, so I want that in there. If I stop at any particular point, s, what am I going to get? So it looks like, okay, when s is 0, I get a square. When s is 1, I get a fourth. Okay, so it's like 1 more power. So it's 1 minus x to the 2 to the s plus 1. Okay, that's what this argument up above is saying. Okay, and so what does that imply? That implies that PS of x is 1 minus x to the 2 to the s plus 1 over 1 minus x. All right, just divide both sides by 1 minus x. Okay, so now what happens as s goes to infinity? Well, remember, the absolute value of x, right, we're going to assume is less than 1. And when that happens, this x, right, well, this is going to be an even power, so I don't worry if it's negative or anything, but you're taking a number less than 1 and raising it to higher and higher powers. Okay, it's just going to get smaller and smaller, and the limit of this piece is going to be 0. And so I'm just left with 1 over 1 minus x, which is that's just radical. I just think that's amazing. All right, so we're going to need this result for the last result of the day. Now, I am so thrilled that I get to show this result to you because I've been speaking in the problem solving seminar for many, many years now. And I've done a lot of Putnam problems in here, but I have never, ever gotten to do a B6. And today we are going to do a B6. All right, none of this B1, B2 stuff for us. No, no, no. We're going big or we're going home. Right, Dr. Ichinose? All right, so this is from the Putnam 2016 B6. And it almost feels like it was designed for this talk. So it's going to be a little more complicated of a sum. Okay, we'll go from 1 to infinity. We're going to have an alternator, and then we'll divide by this k. But then we're going to multiply by another series, n will go from 0 to infinity. And we're going to have 1 over k times 2 to the n plus 1. Okay, so I can imagine being in the Putnam room and getting this and going, okay, I can start with B1 and just sit on that for a while because B6 ain't going to happen, right? I mean, this is pretty crazy. They're not even saying decide if it converges or not, right? It's just, oh, evaluate this. Okay, but we have the tools now. We have the tools. So the first thing, even though there's no immediate geometric series here, I still can play this reciprocal translation lemma game with this piece here. Right? So 1 over k times 2 to the n plus 1 by the reciprocal translation lemma is the integral from 0 to 1 of x raised to this power, but then you subtract 1. So that'll be k times 2 to the n. Okay, and so this summation, right, I can now replace it with a summation of an integral. Okay, now this piece here, I could move that inside and outside of this summation if I wanted because it has nothing to do with n. And so I'm just going to make one little observation on the side. This is another very useful thing to know going into the Putnam exam. So I'm going to write down 2 different series that might show up here. So one of them, I'm going to use this, forget the integral for a moment. I'm just going to use this power of x. So this is over k. And then there's another one where we start where k is 1. And it's the same thing. X, k times 2 to the n over k. So I have these 2 series here that, depending on how I would order these summations, I might see that on the inside. Oh, that's a good point, Dr. Chinose. Yeah, let me finish this point and then I'll remind everybody. Okay, so the point of it is you can use, well, whatever your favorite test is, say the ratio test. Okay, so use ratio test to show these converge absolutely. Okay, now when you're in Calc 2, they usually will mention this absolute convergence, but you're usually not so worried about it. You're just thinking about just the convergence part of things. All right, but this absolute convergence is super important when you're dealing with series, and particularly when you have multiple copies, right, of a summation, because if you want to reverse the order of those summations, it's absolute convergence that you're looking for. So knowing that these 2 series converge absolutely is going to allow us to rearrange these series any way we want. Okay, so I'm just going to write down here and then I'll answer Dr. Chinose's question. Oops. So using this, so this allows us, to swap the order of summation. Okay, and so I'm going to rewrite in the following way. I'm going to pull the integral all the way out. I'm going to put the summation over n first, then we'll do the summation over k, and then we have all this stuff inside. Okay. So for those of you who are new to the problem solving seminar, one of the main activities of this problem solving seminar is preparing for an exam that is held every year in December called the Putnam exam. It is a math examination just for undergraduate students. It is in mathematics, of course, and it is notoriously a very difficult exam. You get 12 problems given over a 6-hour period with a break in the middle after the first 3 hours. And in this morning session, you get 6 problems, A1 through A6, the afternoon, B1 through B6. And roughly speaking, the problems are ordered by difficulty. Now, that isn't always accurate. Like, you may find a really clever solution to A4 and A2 you just can't solve. But generally speaking, if it's A6 or B6, it's a pretty challenging problem, and they expect everybody to get it wrong. So that we can do one of these is really, really fun. Okay. Now, why did I arrange it in the order I did? Well, it's because every time I looked at this stuff over here, in my mind, I was actually doing a little bit of a rearrangement. In my mind, I was rearranging it like this. So rearranging it as x to the 2 to the n to the k power. Okay, which by normal exponent laws is the same as x to the k times 2 to the n. All right. So what's the deal? Why am I so interested in writing it in this way? Well, another thing that we saw in Calc 2, and this, by the way, is for those of you who don't know about the Putnam exam generally is not asking you to know a lot of deep mathematics. It's just asking you to think very deeply about the mathematics you know. So usually you can solve a lot of problems just by knowing some calculus. So in your calculus courses, you'll learn about something called Taylor or Maclaurin series. And oops, missed something here. The Maclaurin series for the natural log of 1 plus x is actually given by this formula here. So this inside bit, the only difference is you have x to the 2 to the n. So this is actually ln of 1 plus x to the 2 to the n. Okay, that's unexpected, but nice. So now what do I have? I have a summation of logs. Hey, isn't there some weird property when you add logs together? Like if you have log of x plus log of y, isn't there's some way to put those together? Right? Yeah, right. So the sum of logs, right, is the log of the product. So here I have a sum of logs, so that's the log of the product. But look at that product. We have seen that product, right? Quite recently, in fact. That product, right? 1 plus x to the 2 to the n, that is precisely our alternate version, right, of 1 over 1 minus x. This is the product form of a geometric series. Oh, how nice is that? So this bit here is just 1 over 1 minus x. Again, we have to assume that x has absolute value less than 1, but that's okay because we're integrating from 0 to 1. So that's not a problem. Okay, so ln of 1 over 1 minus x, what can we do? Well, let me rewrite that as, again, using a log property. This is negative ln of 1 minus x. And now we have just reduced this problem, this A6 or B6 Putnam problem, down to integrating that function. Okay, so this is like the denouement, right? Okay, we've hit the climax, and now we're just going to finish, right? Okay, I can pull this negative out front. What kind of technique would I want to integrate ln of that? Well, let me tell you what. On the Putnam exam, I wouldn't want to have to worry about any technique for doing this. You should know going into the Putnam that an antiderivative for ln of x is x ln of x minus x. That's just one thing to put into your mental toolbox, right? That'll make your life a lot better, right? Not having to do integration by parts here. So what does this end up being? Let's see, I guess that'll be 1 minus x times the natural log of 1 minus x minus 1 minus x, evaluated between 0 and 1. So you can see I'm using this formula, and honestly, there should be an extra minus that comes out of this, but that gets killed by that minus. So we're okay. Now, this is actually an improper integral, and on a Putnam, you would want to mention that. Why is this improper? Well, you're going to have to evaluate this at 1, and ln of 1 minus 1, well, that's ln of 0. That doesn't work so well. Okay, but what's happening near 0? Well, with a natural log function, you see near 0 it goes to negative infinity. But what happens here with the 1 minus x? Well, that goes to 0. So it's just a matter of who wins, right? Do polynomial functions go to 0 faster than the natural log goes to negative infinity? And it turns out polynomials do. How do you prove it? Well, you can, for example, use L'Hopital's rule. Okay, so by L'Hopital's rule, okay, this part is going to go to 0 as x goes to 1 from below. All right. So there's not much that's going to be left over then. So what happens? This part goes to 0. This goes to 0 at 0. That goes to 0, and then you just get a 1, right? So you're going to get minus, but minus 1. So this whole thing equals 1. So that's actually the answer to the original problem, 1. Yet another crazy way we like to write the number 1 in mathematics. Okay. Whew, we solved a Putnam a B6. I'm just so happy about that. Let me quickly show you what I'm going to put into the chat. I kind of went overboard preparing this talk. So you can see here I have supplemental problems and complete solutions for you. So the first ones are going to be more like the technique number 1, and then at some point it'll go over to the technique number 2. One thing I just want to point out as we go through this, okay, at some point things get really hairy. Yes, so starting with 15, I thought it was unnecessary but neat that we could use this technique to show that the harmonic series diverges, but it's not all that impressive because the integral test does the same thing. But I said, well, if you can do the harmonic series, can we do the Basel series? So the Basel is where you replace 1 over k with 1 over k squared. And it turns out with a lot of effort, I could. And so I do a bunch of stuff, and this is probably good study stuff. It really has nothing to do with my talk per se, but it's probably good stuff to read and practice a little bit. But at the very end, well, we actually find the arcsine power expansion, which turns out to be pretty tricky. But at the very end, I'm able to give a solution to the Basel problem utilizing these techniques a little bit. In particular, you'll see here, I'm starting with this series that just has, just a little reciprocal, and using something a little different than the reciprocal translation lemma, but related, I turn it back into an integral. And then it's actually not a very hard argument, right? As long as you build up with all this other garbage, it's not that hard. So, and let me see here. Yeah, so I'm just going to put that into the chat. So if you want to take a peek at that. Now, Jorge in the chat is asking a question. If you were to say stop without mentioning this improper integral stuff, how many points out of 10 would you likely to get? I'm probably not the best person to answer that question. I think, you'd probably do okay on a B6. I don't think they're going to give you like 1 point on this one if you have this full solution but don't mention it's an improper integral. On the other hand, you're probably not going to get a full 10 out of it. But even if you just say like it's an improper integral and this limit is 0, I don't expect that you have to write every detail L'Hopital's rule, but maybe Dr. Suchava has a better feeling for that if he wants to weigh in.